A sequence AN is a bounded sequence if it's bounded below and is bounded above. So that is a definition from the textbook, but you can simplify it to say that, oh, there exists a number lowercase m such that m is less than or equals to an for all n. Okay, so that symbol is for all n, every. Similarly, if there exists a number capital M such that an is less than or equals to that capital M for every n, then it's bounded about, right? So sometimes we will call little m to be the lower bound. Okay, a lower bound, not the lower bound, because that's meant once you find a lower bound, you can make the number smaller and get another lower bound. And capital M is an upper bound. So that is a definition of a bounded sequence. And a sequence is not bounded. Or if a sequence is not bounded, then it's an unbounded sequence. And I'm going to give you examples, okay? Unbounded sequence example. So for example, the sequence n, okay? The sequence n, what does it look like? N equals 1, 2, 3, and so on. You can never find a number or a upper bound to bound it because n can go to infinity. But you notice that it is bounded below. All terms are greater than or equal to 0. Or all terms is greater than or equal to -1, right? So it is bounded below, but it's not bounded above, so it's unbounded. Okay? Another example, -1 to the nth power times n. Okay, so that, what happened? So when n equals 1, we get -1. When n equals 2, we get 2. When n equals 3, we get -3. When n equals 4, we get 4, and so on. It's alternating. So it doesn't have a lower bound because it can go to -infinity. It can also go to positive infinity. So this one doesn't have a lower bound or upper bound, and it's unbounded. So unbounded sequence, it's just that it has to fail one of the requirement, okay? But for a sequence to be bounded, example, right? For a sequence to be bounded, it must have a lower bound and upper bound. So for example, 1/n. So this is just 1, 1/2, 1/3, and so on. It is greater than or equal to 0 each term, right? 1/1000 is still greater than 0. And each term, you can guarantee that each term is less than 2, okay? Is less than 1.1 also. But we can say, okay, all the terms are less than 2. That's true. So in this case, we have a lower bound and we have an upper bound. So we call this sequence a bounded sequence. So now we can take a look at example. Oh, maybe one more theorem. So in order to understand the theorem, we need that definition, right? If a sequence an converge then it is bounded. Okay, so we are not going to prove this. The proof of this, you will learn about it if you take advanced calculus. It's pure math major. But before then, we're not required to prove that. I give you the idea of the proof though, okay? And then in my picture. So you have an n axis and an an axis. So when n equals 1, a1 right here, a2 right here, a3, a4, a5, a6, a7. It can be anywhere, but as long as my tail is converging to a number, or maybe I can make it a little bit more interesting. So it's converging to this line right here. That's my L line. We call this AN converge. So we have this picture, we have AN converge. Then it must be bounded. Why? Okay. So the tail is always within epsilon of L. So it's L plus epsilon and L minus epsilon. That's the definition of convergence, right? So it has to be within epsilon or L, so we don't need to worry about the tail. And then in the beginning, there's only finite number of terms that we need to check. We take the max of those terms plus 1 to be my capital M. And I take the minimum, okay, of all those terms, finite number of terms, and subtract 1 and be my little m. Then I can prove that the sequence is bounded. So that's the idea of the proof. Okay, you have to write rigorously and mathematically sound, but this is the idea. Okay. So we have that theorem, and we have one more theorem. Now, so it's a pretty important theorem. It's called the monotone. Convergence theorem. You don't need to prove it, but you need to understand what it means. Okay? If AN, that sequence is bounded, and there exists okay, an integer a0 or n0. Sorry. So an index n0 such that this sequence is monotone. What is monotone? It means it keeps increasing, never change, it always increase, or it keeps decreasing. Okay, it cannot decrease and then increase and then decrease. Okay, so it's monotone for all n greater than or equals to that index n0. Then the sequence AN converge. And my picture earlier will see give you the idea, right? So you see AN going up and down in the beginning, but once it passes a certain index, okay, as you go further down on the sequence, so as you go further down in the sequence, maybe this index is a n0, it starts to monotonically increasing, right? So each term you keep getting bigger and bigger, but it's still bounded. Then we can prove that the sequence is converged. And the proof is harder. Okay, so again, you will learn it in advanced calculus if you take that class. So we just need to understand the theorem and be able to apply it. So we're going to take a look at example 5.6. Using the monotone convergence theorem, we for each of the following sequence, we want to use the monotone convergence theorem to show the sequence converge and find its limits. Okay, so an easy one, part A, we have 4 to the nth power divided by n factorial. Now earlier, I already mentioned exponent doesn't grow as fast as factorial. So the limit, before you even calculate it, you should know is going to 0, okay? So that should be the limit, but we're going to use a monotone convergence sequence to prove it, or at least prove that it has a limit. Anyway, we still need to find it. So you can write out the first few terms. So when n equals 1, you get 4 over 1 factorial, so you get 4, and then you get 8, and then you get 32 over 3. So you just follow the textbook and calculate the first few terms. So at first, the terms increase. However, at the tail, okay, it decreased. And in fact, the term decreased for all n greater than or equals to 3. And why? Okay, you can break down the formula, right? So an, find a relationship of an and a sub n minus 1. Or you can find the relationship of an plus 1, as the textbook show you. Is 4. So replace n by n plus 1. So n plus 1 factorial. So again, the index is n plus 1. So everywhere you see n, you change it to n plus 1. So what you get is, okay, so n plus 1 factorial is the same as n plus 1 times n minus 1, and so on. So it's n plus 1 times n factorial. And on the top is 4 to the n plus 1 power, so it's 4 times 4 to the nth power. And you will realize this term is just an, okay? So that is 4 divided by n plus 1 times an. So what it tells us is that an plus 1 divided by an equals 4 over n plus 1. And as long as n is greater than 3, so, or let's say you plug in n equals 5, you get 4 divided by 5 plus 1, right? So 4 divided by 6, you get a fraction. It's smaller than 1, okay? For all n greater than or equals to 3. So what does it mean? It means an plus 1 divided by an less than 1. So in that case, you multiply both sides, right? So we have this is less than 1. So multiply both sides by an. You see, the sequence is decreasing. And the sequence is bounded, right? When you write out the sequence, you realize this sequence an. So now we have monotone. Okay, the sequence is decreasing at some point, and we have this sequence an each for all n is bounded about by what is the biggest number you see in the first few terms. 8. You say, oh, it's always less than 9. It's at least 0, right? So it's bounded. So we have both condition checked. So the monotone convergence theorem guarantees that this sequence AN converge. So now we need to spend all our effort into finding the limits. And now the problem with the finding the limit is you cannot use a L'Hopital's rule, even if you have infinity over infinity. Why? How do you take the derivative of n factorial? Think about that. Okay, so that is not going to work. So that's why like just merely taking the limit is not convincing, even if we know the limit is 0. How do we convince everyone that the limit is 0? So what we need to do is we use a relationship that we find for AN plus 1 equals 4 over n plus 1 times AN. We use this. We take the limit as n goes to infinity on both sides. And why is this smart? So you think about that. Because the monotone convergence theorem guarantees that this sequence converge, we will know that AN will converge to a limit L. And that's why we apply the theorem. Okay, not find a limit first and then apply the theorem. We apply the theorem first and then find a limit. And the whole point of it is because we cannot take a limit when we have factorial. So because monotone convergence theorem guarantee that the sequence converge to L, it means this piece is L, and this piece is also L. Okay? Now what is the limit of 4 over n plus 1? So it's 4 over infinity is 0. So what we have is L equals 0 times L. And 0 times anything is 0. That tells us L equals 0. So we know, okay, this sequence AN converges to 0. That's how we prove it. I will go over part B in the next video.